continue with the classification today. Alright, so today we will cover some more classifiers. So we'll basically cover a very basic naive based classifier that's quite easy to understand, and sometimes it is quite powerful. Okay, and we'll also briefly cover SVM and KNN in very brief. We'll just give some examples in scikit-learn. So in the last session, we looked at the decision tree classifier, right? So we looked at the entropy-based attribute selection criteria, and there was other criteria like Gini and all that we are not covering. Okay, but there are other criteria, but this is one of the most important one which is used. Okay, entropy and Gini are two of the most used criteria for splitting a node in decision tree. So in the last session we covered about that. We also covered the conversion of a nominal or categorical variable into dummy variable. Okay, just so that all the variables are treated equally, and they can all and the decision tree can be built properly without having to convert them. So it is like a one hot encoding for every nominal or categorical variable. And finally, we looked at how it is done in scikit-learn, and we also actually created a tree. Okay. Now, one more thing, in the last session, in the demo of decision tree classifier, when we are using this, we created this tree. So if you run that code a few times, you will see that each time it is creating a different kind of tree. Just try it out a few times, and you will see that a different kind of tree is created each time. Okay, so that happens because if there are more than one ways to do something, it will randomly select one of the ways to do it. Okay, so if, for example, if there are two variables, okay, and the split can be done on either of these because they have equal information gain on splitting. In that case, any one of these two variables can be selected randomly. Okay, now if you want that for every node, if you want to get exact same tree, for example, maybe for duplication of your results, right? Suppose you want to reproduce the result again later on. So in that for that, in the decision tree classifier, when you call that and you create that decision tree classifier, there is an option called random state. Okay, just set random state to some integer. Okay, random state is equal to 0 or 1 or 2, something, some fixed. So as long as you always use the same number and same data set, you will see that the same tree is created every time. Okay, random state is equal to some fixed number. So that is kind of seeding the variable. Okay, the variable which selects one of the options randomly. Okay, if that random number is fixed, you will see that if the seed is fixed, you will see that always you will get the same tree, even if you run it multiple times. Even if you run the code multiple times, the same tree will be created again and again. Okay, so this we covered in the last lab. Okay, and today we look at one of the very basic classifier, which is not as sophisticated as others, but it uses something called Bayes theorem, right? Bayes theorem for probability, the conditional probability. So it is naive Bayes classifier. It is naive because there are certain assumptions that it makes about the kind of data. Okay, we will discuss those assumptions and all, and because of that, those assumptions that it makes, it is called naive. Okay, but it's quite a powerful classifier, and in practice, it is often found that the assumptions that it makes, they are not as bad as it seems. Okay, so in practice, the assumptions sometimes they work quite well. Other times they may not work as well, but in a lot of cases these assumptions are good. Okay, they work fine. And Bayes is the Bayes theorem that is used. So it is an Bayes classifier that we will discuss today. So before that, let's look at the Bayes theorem just to recap it. And this is a very popular example that is often discussed when we discuss Bayes theorem. Okay, how something that seems very obvious in the beginning is not so obvious. So the example here is, maybe many of you might have already read about this example, but anyway we'll just revise it. So what is the example is that a patient goes to see a doctor. Okay, so a patient is in certain region. Okay, let's say a certain region is there, maybe certain island with a very limited number of people. The population is, let's say, 10,000. Now he goes to see a doctor, and doctor performs a test. The test has 99% accuracy or reliability. Okay, so 99% reliability means if the person who has come to visit the doctor, if he has the disease, okay, then 99% of the time the result will come out to be positive. Okay, it should be positive. So 99% of the time it comes out as positive. On the other hand, if the person doesn't have the disease, then 99% of the time it will show negative result. So it is 99% reliable, okay, in both positive and negative case. Now there are certain other condition here that only 1% of the people in the region are sick. Okay, it's not a very prevalent disease. Okay, it's not quite common, and it is known. Okay, it is known to us or the doctor that only 1% of the people in this region, they are sick with this particular disease. Okay, or who have this disease. Only 1% out of the total population. Now, let's say the person has the test has been performed on the person, and the result comes out to be positive. Okay, result is positive. Now, what is the probability that the patient actually has the disease? Okay, so the probability of the patient actually having that disease, that rare disease, given that the test has come out to be positive. Okay, so there is a conditional probability that the disease is present, given the condition that the result has come out to be positive. So according to the conditions above, it seems like the probability or the chance of the person being sick is 99%, because the result is 99% reliable, right? And if the person has disease, has come out to be positive, there is 99% of chance that the person actually has the disease. Okay, and now you have to apply the Bayes theorem to find the probability that the patient actually is suffering from the disease. What is the probability given all these conditions that the result has come out to be positive? What is the probability that the person has actually the disease, is actually suffering from the disease? So the Bayes theorem looks like this. So given that the outcome of the test is positive, so A is, let's say, A is the event that or A is the variable that signifies that person has disease. The test has come out to be positive. Okay, so A is, you can say, test is positive. Okay, test is positive. That is A. Okay, and let's say you want to find out C. C is the, so just C is the case or is the event that the person has disease. So taking this separately, it's like Probability of A will be the probability that the person is positive, the test is positive, and the probability of C will be that a person has disease, suffering from the disease. Okay, when it says PC given A, okay, it means what is probability of disease given that the test has come out to be positive. Okay, and according to the Bayes theorem, the probability, this conditional probability is given as probability of A given C. That is, we can see that now the condition is reversed. Probability of A given C multiplied by the probability of C and whole divided by the probability of A. Okay, so it is like simplified. If you just cross multiply, you'll see that you get probability of A given C multiplied by probability of A is equal to probability of C given A multiplied by probability of A. So that is that is another form of the Bayes theorem. Okay, when you want to find the probability of A and C, okay, and they can happen in any order. Maybe let's say first find out what is the probability of C. So find out probability of C, that is PC, and then given that C has occurred, what is the probability of A? So that is probability of A given C. So if you multiply these two, you'll get probability of A C, right? A given C into C. And other way of saying that is if A has happened, okay, if probability of A is known, then if you find probability of C given A, that is also mean the same thing. Okay, so probability of, so if you just take A down in the numerator, in the denominator, you will get this form of the Bayes theorem. It's the most common representation. Okay, so now in this case, what is the probability of A given C? So let me just wait for your answers. What is the probability of A given C? No, don't give me the answer. What is the meaning of A given C? Probability of A given C is probability that the test is positive given that the person has disease, right? If the person has disease, given that the person has disease, what is the probability that the test will be positive? So it is given that it is 99% reliable. Okay, that means probability of person having testing positive if he has the disease is 0.99. Is that? Okay, the person testing positive given that he has disease is 0.99. So that is probability of A given C. What is the probability of C? Probability of a disease. Now it is known that it is 0.01. It is 1%. 1% is 0.01. 1 by 100. Okay, and what is the probability of A now? Probability of A. So A is that the person has tested positive. So there are two ways the person can be tested positive. One way is when he has the disease and he tested positive. The other way is he doesn't have the disease but still he gets tested positive. So there are two ways, right? So probability of testing positive given that he has disease. Okay, so if you multiply this by the person having disease, that is one way. Plus there is one more case when the person tests positive okay, even if he doesn't have disease. So I'm just calling it C minus or C bar to signify doesn't have disease. So multiplied by what is the probability of a person doesn't have disease, that is probability of C. Okay. So if you solve this, you'll get, yeah. So many of you have already shown the answer in the chat box. So it is again 0.99. So the first factor is same as we have written earlier 0.99 into 0.01 plus the second sum here is probability of A given C bar. What is the probability of the person testing positive given that he doesn't have disease, right? So it is given, it is known that if the person doesn't have disease, the probability of him testing negative is 99%. Okay, so that means there is 1% chance that he will test positive. So that is 0.01. Okay, into what the probability of the person not having disease. Okay, so now that is the general case. We know that 1% of the people suffer from the disease. So that means 99% of the people don't suffer from that disease. So that is 0.99 is the probability of the person not suffering from disease. Okay, now the condition is known. So random person is suffering from disease is 1%, not suffering from disease is 99%. So if you solve this, you'll get how much? 0.5. So probability of C given A will come out to be 0.5. Divided by, of course, you have to solve the numerator by denominator, and you'll get your answer, that is 0.5. Okay. So the probability that the person has the disease, even if the test comes out to be positive, is 0.5 only. Okay, so it's kind of just random guessing, isn't it? If you just randomly guess and you just say not diseased, that will have higher probability. Okay, so anyway, it's 0.5. So randomly guessing is not 0.5. It is only 1% people suffering from disease, so it will be less. Okay, so 0.5 is the probability of a person suffering from disease given that test is positive. Okay, so that is not a very high probability as it seemed. It seems that the probability would be 99%, but here it is only 50% probability. Okay, so that's why such cases actually exist. Right, many tests have certain reliabilities, and because if the disease is very rare, so you'll see that more than one tests are performed. Okay, so that's the reason, because the diagnosis has to be correct. The doctors have to be sure that the disease is present, so that a proper medicines can be given, proper treatment can be performed. Okay, so many times you'll have 2-3 tests that are performed, and if all of them are giving some probability, some big chances or some reasonable probability, then only the treatment starts. Okay, so this is the Bayes theorem. Now let's look at an example of this. Okay, if this formula is not as intuitive, let's look at an example. Same reason, and the number of people is 10,000. Okay, so if you just create a contingency table like this, that is, columns are diseased or not diseased. So out of 10,000 people, you know that 1% are having disease, right? So that means 1% of 10,000 is 100. So 100 will have the disease, and the 99% will not have disease. So these are two columns. Okay, and then test is performed. So test comes out to be positive or negative. Okay, now it is given that if the person has disease, 99% of the time it will come out to be positive. So out of the 100 diseased persons, 99 will test positive, 1 will test negative. Right? And out of the people who are not diseased, okay, how 99% will be tested negative. So 99% of 9900 is 9801, and 1% will still test positive even if they don't have disease. So 1% of 9900 is 99. Okay, so 99 people will still test positive even if they don't have the disease. Okay. So if you just look at this contingency table, and then if you have a look and tell the probability that what is the probability that a person who has tested positive, what is the probability of him having the disease? Okay. So tested positive is this column, that is 198. Okay, and so this is 198 which are tested positive, and out of this, how many have diseased? 99. Right? So that is 99 by 198. Right? If you just try to find the probability, it is the favorable condition to disease. What is the number of people who have the disease? 99. Out of how many tested positive? 198. Right? So out of 198 people who have tested positive, 99 have the disease, or you can say the probability of a person having disease is 99 by 198, which is nothing but 0.5. So you'll get the same answer. We just solve it by using an example like this also. Okay. All right. So this is Bayes theorem. Now let us look at an example, an application of Bayes theorem, a naive Bayes theorem, or naive Bayes classifier. Okay. So one of the first use of naive Bayes classifier was in, or the important use, or a very interesting use that we will discuss today. We'll also look at one implementation of that is in spam versus non-spam classification. Okay, whether a mail or whether a text, SMS, a message, whatever text, whether it is spam or not. So you want to create a classifier, a binary classifier. Okay, that means spam or not spam kind of classifier. Okay, so not spam is also called ham, HAM. So spam or ham. So given any message, you want to predict whether it is, or you want to classify whether it is spam or not spam. Okay. Okay. Naive is a scientist. Why is it called? Oh no, naive is not a scientist. Okay. So Bayes was the person. I think he was some priest or someone, a mathematician, who came out with this formula. But naive Bayes, it's called naive Bayes because the conditions. Okay, there are certain assumptions it makes. Okay, and those assumptions are just naive assumptions. They are just basic assumptions. So that is called naive Bayes. Okay, there is no scientist with the name of naive. Okay, Bayes was the original person who came up with this probability, or after whom this is named, is Bayes theorem. Okay. But naive is the class. Naive Bayes is the classifier. It is just some, you can say, simple. Naive is, in the meaning of naive here is simple. Okay. A simple Bayes-based classifier. Fine. So there was a question. Naive is a scientist. Why is it called so? Why is it called naive? So there was a question someone asked. So naive is because there are certain assumptions which are made. Okay. And those assumptions are simple assumptions. So naive here means simple. Fine. So let's look at the example of a naive-based classifier that can classify spam versus ham text or messages. Okay, and let's look at a theoretical example first, and then we will look at a bigger example with a program, with a Python code. Okay, so in this first in this example, we have only 5 examples are there in this corpus. You can say in this, you have only 5 documents, okay, or 5 examples, and they are labeled either they are ham or spam. So there are 2 ham documents and 3 spam documents. Okay, so out of 5 documents, 2 are ham, 3 are spam. So obviously the probability of ham is 2 by 5. Probability of spam is 3 by 5. Okay, and now you want to find. So what it does is, what naive Bayes classifier or the spam classifier, what it does is it looks at the probability of each word. Okay, it looks at each word in the text, or each significant word in the text. Okay, And then based upon the whenever any document has to be classified, it will look at each word and whatever probabilities it has learned for each word, whether it is how much probabilities that a word is present, whether word is a spam word or a ham word. So that probability he has to the naive-based classifier learns that probability, okay, from the training set, and then whatever probability it has learned in the training set will be applied during testing, okay, during on the new document. So in this case we have 5 training documents and 1 testing document. You can see there's 1 testing document. You want to find out whether it is according to naive base, whether it will be a spam or ham. Okay, but before that you have to train the naive base classifier. Okay, you have to find out the probabilities. So for that, a very common thing that is done is called Laplace smoothing, okay, which is very often performed on text set. Because what happens is that if you look at this example again, okay, so if so in this way you can say that bad is not present in a ham document, right? The word bad is not present in the ham, none of the ham documents, okay, it is not present. And similarly word good is not present in any of the spam, okay. But it may happen that certain spam documents in the future, okay, or there may be some spam documents which are not in the examples, but they may be available, they may be present somewhere, okay, and those spam documents might contain word good, okay, or ham documents might be there, okay, which contain the word bad, okay. So if you just go by this, then what is the probability of a word say bad? What is the probability of a word bad? I'm just writing it as a string bad, given that the document is ham. Just from this, okay. If the okay, there's a question. If the sentence is not good, actually it is bad, then what will happen? Yeah, don't worry. We are looking at all the examples. Okay. So what in this case? So there's a question that we will discuss later. Right now, let's continue with this. So what is the probability of bad, given that you know that the document is ham? So just looking at this training example, what is the probability of bad? Bad is not present, right? Bad is not present in any of the ham documents, so it will be straight 0. Okay. Or similarly, if you look at probability of good, given that the document is spam, right? And that is also 0 because the word good is not present in any of the spam documents, right? So if any of this it becomes 0, so when you solve the naive base, when you create the model based on naive base classifier, you'll see that the entire probability becomes 0, okay, because of one missing word. So what is done normally is what is called Laplace smoothing, in which to the count of every word, okay, whatever the count of every word in a particular document, 1 is added to the count. Okay. So what happens is, let's say you want to find out what is the probability of bad. So what is the count of bad in ham? It is 0. Okay. But in Laplace smoothing, you just add 1 to every count. 1 to every count. Okay. And divide it by the number of words which are present. Okay. There are 2 goods and 1 very plus bad. So there are 2 goods plus 1 very plus 0 bad, right? But because you are doing Laplace smoothing, so we'll again add 1 to each of the counts. Add 1 to the count of good, so it becomes 3. Add 1 to the count of very, it becomes 2. And add 1 to the count of bad, and it becomes 1. Okay. So these ones are added in the count of every. So what are these? These 3 are the vocabulary. Okay. So again, I think I didn't tell you. So you have to find the complete vocabulary. Okay, so complete vocabulary here consists of only 3 words: very, good, and bad. Right? There is no other word present. We are not considering the punctuations and all. Okay, they are normally ignored. So to the very, one word is very, then good, bad. Only 3 words are there. So we are just trying to find. We are just counting the number of words present in ham. So probability of word bad, given that the document is ham, after performing Laplace thing, will be given as this probability. Okay, so this is, you can see, it is 1 by 3 plus 2 plus 1, 6, is it? So it is not 0. It will come out to some small number. Okay. 0.1 something. 6 on the 6. 6 maybe you can say 0.17. Okay, there is some probability of bad still. So this way you will, even if the word is not present, you will still give that word some small probability of being present in the particular kind of document, in a particular labeled in a particular class. Okay, so here ham and spam are 2 classes, and similarly, now can you tell me, after applying Laplace Laplace smoothing, Laplace smoothing, what will be the probability of word good given that the document is of class spam? Okay. So just tell me the formula. You don't have to solve it completely. Just give me the formula. So what will be the numerator? Now because good is 0, so numerator will be 1, right? Laplace plus 1 is smoothing. Okay. So there are multiple ways of performing Laplace smoothing. Maybe 0.5, 1. Okay, some other number. So for simplifying, we are just, because number starts with 1, so minimum is 1 here. So we're just adding 1. Okay. So 1 is the numerator, and the denominator will be the count of each of the words in the vocabulary. So very is present 3 times. So 3 plus 1 is 4. Then good is present 0 times. So 0 plus 1 is 1. And bad is present 4 times. 4 plus 1 is 5. Okay. So each count is 1 is added to each count. So 1 by 10. Okay. So it is 0.1. Remember, we are looking at these label documents. Okay. Now I hope that question is answered. If the sentence is not good, okay, it is actually bad, then still you have probability for something, right? If bad is already present, then that count is 1 is added to the count. It doesn't matter. Okay. So every word is considered. Okay, the count of every word is considered. Okay. If bad was present here instead of good, okay, the question is, what happens if good was not present here in the first document, instead it was bad? Okay. Okay, we are looking at a meaning. No. Okay, so remember that these classifiers, they don't look at meaning. Okay, they only count what is present or not present. Okay, there is no meaning or something. Okay, they are just individual word based. Okay, so not bad means good, doesn't matter. Okay, so nat, what is the probability of nat? Not, what is the probability of good? That will be looking. Okay, so we are not looking at meaning of the phrase or sentence here. Okay, so let's now look at what is the probability of other words. Okay, so look at probability of very, given that the document is ham. Okay, and then probability of good, given that document is ham, What else? What other property you have to find out? Probability of vary, given that document is spam, and the probability of I think other property we have already found earlier, right? Yeah. So what is the probability of vary being present, given that the document is of type ham? So vary is present once, right? One. So 1 plus 1. We are doing Laplace, 1 is moving. So 1 plus 1 is 2. So it is 2 by. So denominator remains same like earlier. So what is the denominator earlier? So it is vary is 2, good is 2. So 2 plus 1 3, bad is 1, 0 plus 1, right? So 6, right? 6 was the denominator. So 2 by 6. And what is the probability of good? 3 by 6, half. So look at the probability of each word, given that the document is either spam or ham. So just calculate each of the probabilities. Okay, and that is what is being done here. Okay, so we are doing Laplace smoothing, or it's also called Laplace plus 1 smoothing. Okay, so the vocabulary here consists of 3 words. So find the probability of each of the 3 words, given that the document is of type ham. Okay, and also the probability of each of the 3 words in the vocabulary, given that the document is spam. So that is done here. Okay, all 3 probabilities. So you can see that the probability of good, it's not 0, right? Even if it is not present in spam, still the probability of good is 0.1 because of Laplace smoothing. If it was not performed, the probability of good given spam would be 0, and you will see that later in the formula you would have got 0 of the entire naive Bayes classifier probability. So it is not useful. So it is better to should always perform this kind of smoothing as normally performed. Alright. Now let's now look at the document wise probabilities given a certain label. Now here is the naive Bayes assumption that comes into play. So it says that the probability of, so let's look at probability of say DC. So now you want to find out what is the probability that these 4 words are present, given that the document is ham. Okay, given that the document class or the class of the document is ham, so it is given that the class of the document is ham. Now what is the probability of these 4 words being present? Good, and bad, very, bad. Okay. So the assumption here is that they are all independent. So each of the words here which are present, they are independent of whether other words are present or not. Okay, so I am looking at each of the words individually. So it says that probability of these 4 words being present can be found by just multiplying each of the probabilities. That is good being present, given that document is ham, multiplied by what is the probability of bad, given that ham, multiplied by probability of very, and multiplied by probability of bad. So 4 words, 4, just multiply 4 times. Okay, and these probabilities you have already calculated. So this is the naive assumption. Okay, so probability of D6 given ham is probability of each of the words given ham, which are contained in D6. And similarly, probability of D6 given spam will be the probability of each of the words given the spam, multiplication of the probabilities, or the product of the probabilities of each of the word given spam. And these probabilities we have already found in the last slide. Okay, so once you have found these probabilities, So probability of D6 given ham is 0.004, and probability of D6 given that it is a spam document is 0.01. Okay. So now what you want to find out basically is what is the probability of document being spam. Okay. Given that this D6 is present, given that this document is present. So given that the probability of D6, or given this document D6, what is the probability that it is a spam document? Okay. Now here we are applying the Bayes theorem. Okay. So look at the Bayes theorem. Yeah. So here C is the probability of being spam. A is the probability of document D6. Probability of document D6 means probability of the product of the probability of each word given spam. Okay. So okay, so this is the probability of, so probability of D6, sorry, it doesn't mean probability of D6 doesn't mean given. So it just means what is the probability of this document being present. Okay, the total probability. Now here you can see that in this example, in this doctor example, the doctor knows that 1% of the people in the region are sick. Okay, the doctor knows this. Okay, so doctor knows this probability of so what is the, in this formula, what is the probability that doctor knows that only 1% of the people in the region are sick? So let's say in that earlier case, what we want to find the probability that the person is sick, given that the result is positive. Right? So this was the probability earlier that we wanted to find, and we'll apply the Bayes theorem here. Right? So in this, where did we use that condition that doctor knows that 1% of the people in the region are sick? So that is the probability of C, isn't it? Okay, so that was the probability of C here. But now, in this case, what you want to find out is what is the probability of the document being spam given that the document D6 is present, or you can say document D6 is present, document containing those words is available, is present. Okay, so this will again apply the Bayes theorem. Let me just complete this. So probability of D6 given spam. So this we have already calculated, right? What is the probability of D6 given spam? Just multiplying the probability of each word multiplied by probability of spam. Is it? Divided by the probability of D6 in turn. Okay. So in this case, what is the probability of spam? In the example, in our example, what is the probability of spam? I think I mentioned earlier, there are 3 documents of type spam, right, out of 5. So 3 by 5 is the probability of spam, and 2 by 5 is the probability of ham. Okay. So you know this according from this example, you know that 2/5 are ham, 3/5 are spam. So any random document being of type ham or spam, the probabilities are 2 by 5 and 3 by 5, ham and spam. Okay, so probability of spam is is 3 by 5. Right. All right. So this we have already calculated. Probability of D6 given spam, just multiply each of the conditional probability of each word given spam. You have already found out. Okay, and what is the probability of D6? Now this is interesting. What is the probability of D6? Probability of the document. Now remember, in the case of the doctor and the patient, the probability of A was the probability of a person being tested positive, right? What is the probability of person being tested positive? Now here you want to find out what is the probability of this document coming to us, or document being present. Okay, now this is not an easy probability to find out. So what happens is basically this is not calculated. So this probability of D6 remains as it is. Okay, and you'll see that relatively you can still, even without calculating probability of D6, you can still get the result. Okay, and that's what you will see here. Okay. So you'll see that if you apply the Bayes theorem, probability of ham given D6 that you find out, and probability of a spam. Okay, and whichever has the higher probability given this document, we'll label it as that. Okay, the higher probability will win. So when you apply this Bayes theorem, you'll see that the denominator probability of D6 is not calculated at all. Okay, in many cases this probability is not easy to find out, so it is just left as it is. And even without it, because both of them, this probability of D6 is common to both of them. Okay, that is probability of ham given D6 and probability of spam given D6. So it is not calculated, or it is not required to be calculated. Okay, and still you get the result because of the denominator. Okay, so numerator will give you the result. So in this case, you'll see that the probability of ham comes out to 0.0019, and probability of spam is 0.006. Okay, so obviously here the probability of spam is higher. Okay. So probability of spam is higher. So that means the document is more likely to be a spam document. Okay, so it will be classified as spam. Now it's a very simple example. Okay, a very contrived and very simplified example. So it is not as obvious. Okay, many times you'll not get as clear cut. Okay, here it looks like, because you can see that bad is present 2 times in the test document and good is present only once, and then there is there, so it looks like it will be a spam. Okay, the document is very big. Okay, or the size of the training or the data set is huge, then you cannot just look at it and find out the class. Okay, so in that case, the naive Bayes classifier the tools, they're useful, and one such tool that we'll be using is again using Python and sklearn. We'll see how we can create a naive Bayes classifier. So hopefully you'd have downloaded the data set that I mentioned. I also mentioned about NLTK, and did you get the mails? I mentioned about downloading NLTK and one package for tokenization. Okay, but as it comes out today, we will not use that. Okay, we will not use NLTK. We will not perform any pre-processing on the data set. We'll directly use the data set. We have also downloaded the data set, the spam versus ham data set. It contains a few thousand of spam versus non-spam labeled SMS messages. Okay. So we'll use that data set to see the result of naive Bayes classifier, and also we'll look at some more classifiers, that is SVM and KNN, on the same data set. Okay, so we'll just take a small break, and then we'll look at the practical examples. Okay, even though that it's not a huge, it's about 5,000 some data set, but still it's not a toy, not a obvious data set. Okay, in reality, in real world, the spam versus non-spam data set will have like millions of examples. Okay, and it will keep on growing continuously. Right, whenever you click on a mail that you want to label a mail as spam, right, or junk, immediately that will go to the so that kind of will give a new example. If it is a unique example, it will be taken by the system, by the email provider, and retraining will be performed on the classification, on the classifier, so that in the future, if again such kind of mail comes to such person, it will automatically go to the junk folder, or at least your junk folder, because it may be specific. The classifier may be specific to the person. Okay, so for you that will go to junk. If it is maybe labeled as junk by many, then maybe it will go to junk for all. Okay, so we'll the junk folder. So we'll just discuss about the spam versus ham classifier using Python after a short break.